And we're now going to move on to time frequency analysis and coherence. So if I look at time frequency analysis, I need to check why, first of all, why do I want to do time frequency analysis? Well, one reason is that I can reveal signal that is related to the stimulus, but it's not necessarily time locked to the stimulus. And if I average that kind of signal, then the not time locked signal will get lost. I can get some more information about my data if I use time frequency analysis, because I keep this information about not time locked data. Also, if I want to calculate coherence between brain regions, this requires a time frequency data decomposition. This is a little example. So I have an evoked signal here, and I can see in the time frequency decomposition where I've now got my time axis on the right, my frequency axis is on the y-axis, and I've got some activation that's indicated by the strength of activation in color coding. You can see the evoked in red and also some induced signal in this time frequency. If I can subtract the evoked signal, and then I can just see the induced signal, which I will not see in the average. Yeah, so we get to the time frequency analysis result via convolution with different functions, which I'll skip for time reasons. And we can use this time frequency decomposed data also as a basis for beamforming solutions and also for coherence analysis. Yeah, beamforming is a nice alternative way of source localization, and in BESA research it's realized as a time frequency beamformer, and that means we allow the source localization of evoked and also induced data. So both stimulus locked and not stimulus locked data, they can be source localized using the beamformer. And the result of the beamformer is a three-dimensional image for the selected time frequency range. Yeah, then talking about source montages again. So if you think of coherence, coherence can be calculated on the scalp. But if we think of a source in the left auditory cortex, it shows signal not just on an electrode above its activation, but also in other areas. So there's a propagation over the scalp of that activity. Similarly, in the right auditory cortex, there will also be propagation. And now if I measure a coherence between these electrodes, C3 and C4, I'm not sure whether this is simply due to some propagation effect of the volume conduction, or whether this is really a true coherence between brain regions. So our approach is to first transform this scalp signal into brain source signals using the source montages, and then reconstructing the waveforms, and then calculate the coherence between these source channels. I need to skip these. So I need to skip the explanation of coherence here. So this is something, it's just a basic formulation of coherence, and instead I'm going to show you some examples in a minute. I just want to mention we have another coherence implementation as well called DICS. This is the dynamic imaging of coherent sources, and it's a method that does not require you to create a source montage. It just works on any data that you supply, any time frequency range, and can be calculated between any pair of voxels in the brain. That's the cortical application, or between the brain and the muscle, corticomuscular application. So it's related to beamforming techniques, and we can perceive it as a source localization technique for coherent activity. What's the disadvantage and advantage between source coherence and DICS? In source coherence, we require a good source model for our source montage. This is influenced by regularization. That's not so good, but the good thing is we can also get some causality information using the phase diagram. In DSCS, we don't need any a priori knowledge on the sources involved. In that way, it's a nearly automated method, but we don't get the information about causality. So both have their pros and cons. And to study the effects of different approaches, we can use a simulated data set again. And this simulation is now based upon 4 different brain regions that are involved. 2 are static to a stimulus. So in the simulation, there was 2 dipoles in the auditory regions that became activated after a stimulus with a fixed offset. And then there was 2 other regions also close to these, but with different orientations, that then became active at a later time. And these dipoles 3 and 4, these have a different onset time, so they jitter in time of onset, they jitter in length of duration, and they jitter in the frequency. So they have a variation in all these parameters. That data set looks like I'll show you in a minute. So this is the raw data. So the raw data show just a standard EEG that onto which we superimposed our simulated data. So trigger number 1 is the stimulus that is then followed by a static response, and the jittering that starts at trigger number 2, and you can see that trigger number 2 is always got different timing with respect to trigger number 1. And if I average these up and show you the result of the average, then I can see if I average with trigger number 1, then I can get this response here, and I can see very little of that oscillatory activity that starts later. If I average trigger number 2, then I can see some of the oscillatory activity, but I can see hardly anything of the static stimulus before. So that's the way we created the simulation. And if I look at this in source analysis, and so if I bring up this one and also the other epoch, I can now load a solution that was created for this. So these first 4 sources, go back. So this is the condition where we averaged the first stimulus, and you can see the first 2 sources here. They show the response according to the stimulus, and then we've got the next 2 sources which should show the oscillatory response later on, but they are very much averaged out. And if I trigger my average according to the oscillatory response, I can see there's some activity here, but not very much before in the first 2 sources. And then I've got my other 5 sources here later that should simply summarize any other activity that goes on in the brain. So if I now apply this to the data, so I'm going to save this as a source montage, this solution, and I'm going to call it AC90 test RC1 because it's got a regularization constant of 1. Then immediately my data set here gets transformed into the source montage, and if I go back to my ACOC20, I can also pick this source montage from the user button. So here it is. But I'm now going to work with the RC0. It's the same source montage. It just has a regularization constant of 0. And so I can see these little source symbols here. And I can see my data have been transformed. And now I'm going to do a time frequency analysis on this. So this is done using the ERP menu in BESA research. So I'm gonna go to edit the paradigm. I'm gonna load the paradigm actually. So the paradigm simply consists of two conditions with averaging the code number 1, number 2. I can perform an artifact scan to get rid of any eye blinks and other electrode artifacts, and I can change the number of accepted trials here. So I've got 84% accepted trials, and then I go over to the coherence tab, and here I can get a trade-off between my time resolution and my frequency resolution in the time frequency decomposition, and the 2 Hz and 25 milliseconds sampling. This is kind of trade-off between best time and best frequency resolution, so I'm going to work with that and start the time frequency analysis. And this is the result of the time frequency analysis, and here I can see that I get my 9 source channels, and I can see the change in activation with respect to the baseline. So the interesting thing is that this channel here, the ACPR and the ACPL, these are the channels that actually have the highest response in the evoked potential, and the ACSR and the ACSL with a big red blob, this is the simulated oscillatory activity that is not time locked. So if I choose to show the waveforms along with this underneath the time frequency plot, I can see that here we've got the high evoked potentials. You can see a little bit of red signal here, but not much. And the oscillatory response is nearly not present in the average, but it's very strong in the time frequency decomposition. So switch these off again. I can now also compute the coherence between one channel and the others by double-clicking on the channel. And I can see that this channel is highly coherent with the other oscillatory channel. So it's got about 0.8 coherence value, and it's got very little coherence with any of the other channels, apart from some noise that is similarly projected onto both source channels and creates some noise coherence. And also I can see some alpha rhythmic coherence at around the 10 Hz range that is present in some channels because we didn't have a very good model for the alpha rhythm. So let's compare this to the scalp coherence. So if I go and pick the reference-free montage, for example, for a standard montage, and do the coherence analysis on this. So I now go back to ERP coherence, start the time frequency analysis, and run through the trials. And now I can see that I get this oscillatory activity in nearly all the channels. And also, if I double click on, say, A1 to get the coherence of this channel with the other channels, I also get a coherence with nearly all the other channels. And this is this volume conduction propagation effect over the scalp that is actually doesn't allow me to distinguish between what is real coherence and what is actually simply due to propagation of activity. Yeah, so this is one lesson that we believe that source coherence is a better approach than using scalp coherence. Now, there's 2 more little things that I find is so important I want to show you before time runs out. One is that we can use a beamformer on this time frequency data to localize activity. So if I find something that I'm interested in, I can left drag around it. I'm going to show you again. So I'll go left drag, and then I can select this image menu here. And now I can decide that I want to compute a beamformer image and I'm going to work with an interval from, say, 450 to 750 and minus 300 to 0, and a frequency from, say, 16 to 28 Hertz, and go. And now it will compute the cross-spectral density across this, and then show me the beamformer result and automatically jump to the highest maximum. So this is the so-called multiple source beamformer. That means it automatically chooses bilateral positions for my voxels that are evaluated during the beamforming computation, and this should be preferable if I'm looking for potential bilateral activation. We also have a single source beamformer, which I can show you too. So single source beamformer looks like this. So it kind of has a much more spread activation over the two hemispheres than the multiple source beamformer. So I can see the two maxima very nicely activated around about where my sources were simulated, and the third maximum is very, very small, so it's negligible here. And then I also want to show one application with real data, and that is the DICS applied to experiment where there was a potential coherence between the cortex and the muscular activation. So I'm going to open a data set. That's an MEG data set now, also in our standard example data set, DICS corticomuscular. So here we have a MEG recording with 151 actual gradiometer channels, and I'm just going to run the time frequency. So what was done is that a subject needed to exert a force against a lever with one of the arms, I think left arm, and then had to try and keep the force steady over some time. And so we've now got, we've inserted triggers during this time when the force was applied, and we can now compute the time frequency, this decomposition of this, where we actually only care about the frequency, and then we will calculate the DICS between the cortical activation and the muscular activation. So after we get the time frequency activation finished, we've got many channels now to show in our time frequency diagram, because it always works on the currently selected montage. And I just want to show the absolute rather than the difference to the baseline. So I'm going to show the absolute power, and I'm just going to concentrate now on the EMG channel. So I'm right-click and show only this channel. This is going to take a little while till all the channels have rearranged themselves, deleted from the display, and the new channel is shown. So it's going to take another few seconds. Here we go. Now I need to scale this up quite largely until the activity comes up. So now I can see some activation, and I can see that at around 15 Hertz there is a band of activity that becomes active, and I can use this band and try and get its coherence with the brain. So image. Now I'm going to use the DICS option here and choose an interval from 0 to 500 and a baseline minus 500 to 0, from 12 to 18 Hertz. Go. And again, now it has to go through the data set again to calculate this cross-spectral density matrix that is used for the DICS computation. And I can now choose what my reference channel is for the DICS, and in this case, because I'm looking for the coherence between the muscular activity that was measured with the EMG channel and the brain, I want to use this external channel as a reference. So OK, and now I get the DICS computation. And yeah, I get indeed very focal maximum in the right hemisphere in the somatomotor area, where my movement in the left arm is coherent with this brain activity at between 12 and 18 Hertz. So we didn't put any assumptions in that. We just used the raw data, and we got a completely automated analysis that showed us this result. And we get a few more activation centers that could also be of interest. Yeah, and so that's also a nice alternative to the source coherence, using this type of coherence estimator. So now this is the end of my quick presentation on the time frequency and coherence. And Ryan, I think we are maybe running out of time. Otherwise, I would have had something about statistics, but we maybe don't have any time left. Is that right?
Yeah. Yeah, I think we have to call it a day for now.
Yeah. So I can just say that we do also have a statistics package that's very powerful, that allows us to analyze the groups that apply the group differences between conditions in either t-tests or ANOVAs, and uses a method called cluster permutation statistics that automatically accounts for multiple test corrections, and has already been used in many publications. And so maybe another time I would be very happy to show you that too. But so now I'll maybe stop and listen to your questions. For resting state, we have a number of we have some new source montages available for resting state analysis. So what we can do is, if I go back to this example file, we have a button here called SRC, where our standardized source montages are kept. And in this we have a subsection called resting state montages, and we have optimized some source montages to analyze the default mode network, and also 3 other networks that have been identified using combined fMRI EEG studies. So if I go to the DMN, then this data is now transformed into default mode network sources. These are regional sources. So we have 2, 3, 4, 5, 6 sources accounting for the different aspects of the default mode network, plus another 6 sources that should account for noise, so for unrelated brain activity. The sources are, you can see a rough representation where they are by right-clicking on their labels. So they are in the different aspects that are relevant to the DMN. This one, for example, is typical for alpha rhythm, and you can see already that it picks up a lot of alpha here. We can then, if you want to study this in time frequency, you can create triggers in regular intervals, and then use these trigger intervals for time frequency decomposition and analyze coherence between the different sources, for example.
Thank you.
You're welcome. Yeah, this is also something we have in the coherence module. So if we go back to the coherence. So instead of calculating coherence, we can also calculate the phase locking value, and this is just available from the toolbar in the coherence module.
Okay, thank you.